40E. Hmm? 40E came from the code, axial compression. Check, there's a flange section. Let me teach you how to use table 11. Let's come again. Let's come again. You guys should calm down now, please. I can't really shout. I can't really shout. So, we have flange first. When you are using this table 11, we have flange. And we have the web next to the flange, immediately under the flange section. We have, once again, flange. We have web. We have categories of, you know, I mean, for the flange, we have when it is like road section category. We have when it is welded section category. We have when it is compression due to bending. We have when it is also axial compression category. Right? For flange, check your code. For web also, you have some things you use to like check the limits. Right? So in this question, we're dealing with axial load. Right? And we're dealing with a compression member. Right? So it means that the 4 categories for the flange, out of the 4, which one are we going to be using? Check your code, check your code. I can't come again. Axial compression. And what is the limit for axial compression? Exactly. Now for flange, what is the ratio you are going to be using to compare to the limits? Exactly. And 2.75, is it not in the limits? If it's in the limits, what can we call this flange classification? Is that fine? That's for when you are doing the entire classification that you use the weakest one. But for this one, we're checking the limits. For flange, we're using P/T to check the limits.
Wait, hold up. The man also used the same parameter, axially loaded, right? But we used 9E.
That's because there was a mistake. It's supposed to be compression, axial compression.
Axial compression.
Yes, this is a compression case and axially loaded.
So he made a mistake.
He also saw it was like it's supposed to be semi-compact.
Okay, but he just went.
He said that understanding is one matter.
Alright, can fire on.
So we have that. We also need to classify the web. And to classify the web, we're comparing D/T to neutral axis at mid depth. To okay, it's also axial compression. So D/T, we're comparing it to 120E over 1 plus 2R2. Right? Check the code. What is R2? Turn your BS code to the next page. R2 is FC over AG 3YW. 3.5.5. Now, when FC is compression, that is when we are having positive FC. For instance, let's say your FC is 20 now. Right? Let's say your FC is 20 and it is in compression. It means that FC will be positive. But if it is in tension, that is, instead of having something like this, you are having something like this. When you are putting it inside any of those R2 or R1 formulas, for this it will be negative. That FC will be negative. But for this, that FC will be positive. Just know that. Now, honestly, we don't need to classify the web. We don't need to classify the web because the flange is already weak already. Exactly. Do you get? So it means that we can just say that the whole entire cross section is, do you get, semi-compact. I mean, they didn't even give us the force. But, sorry. But, if not for the fact that they said that, please, pay attention. If not for the fact that they said that, just find the compression resistance. Because they said just find compression resistance. That's why we don't need this FC. We just need to like find compression resistance. But if they say find the member that would work, we need to assume FC also. Do you get? We'll solve the question. It's not make sense like this. We'll solve the question. Yeah, it's axial compression I'm using. Check it. No, check. Under axial compression, trace it. Yeah, trace it.
But what do we use that generally?
We use it generally when we are dealing with axial compression and moment at the same time. But if it's just moment, we're using the first case for the web. Yes. Let me explain something. Let's say this is our column. And we have moments here. And let's say it is subjected to pure bending. Right? It means that the neutral axis in the cross section will be at the center. Do you get? But when we are now having axial compression and moment at the same time, we will be having stress ratios. The neutral axis will be shifted to another position. So that's when we will now start having stress ratios and everything. Just follow the code. So what do we have next? We have classified the cross section. We now have to find the slenderness ratio. Do you get? Do you guys understand? Hey.
Yes.
Do you understand?
Yes, sir.
Do you understand?
I think they just want to pass.
See. Okay, let me now start. Let me come again. Please, when I'm like explaining, if you don't understand, just let me know. Please. Now, we have gotten E and B. Exactly. We have gotten E. But we have to classify the flange. To classify the flange, we need two things. We need B over T, what we're using to be checking. And we need our limits. This we'll get from the code. In the code, the limit was 40E. So we're comparing 40E with B over T. If B over T is less than 40, if B over T falls in the range of 40E, it means that that flange that we want to classify is a class 1 plastic. But now, the fact that when you now go and classify the web, and to get R2, you can see that we need R2 under axial compression. To get R2, we need FC. Right? Do you understand? To get R2, we need FC. And now, FC was not given, right? So it means that, okay, let me just put it this way. Let me bring the idea that the entire cross member is as weak as the weakest. You understand? And in that, the weakest is, we know we don't use slender like that. It's not even there. So in that, the weakest is already class 3, semi-compact, right? So there's nothing that can be as weak as, except class 4, and we don't use class 4 because of local buckling. We don't use class 4. So it means that the weakest that possibly the web can be also is class 3, right? And because this one was class 3 also, it means that class 3 is the section classification. Do you guys understand this one? Do you understand? Do you understand? Do you understand? I mean, do you understand? I lie. Do you talk? Explain.
You said the member is as strong as it's as strong as the weakest.
And we neglect class 4. It means that the weakest is. Yeah. It means that the weakest is class 2.
Yeah, the weakest can be allowed to use.
Yeah. So, and if this is class 3, if the web is class 3, and also the flange is class 3, it means that everything will be class 3.
Yeah, the whole structure.
And okay, let's say eventually after doing calculation, the web is class 1, and the flange is class 3. It means that it will still be class 3. So that's why we can just say class 3. It's not that it's flange that actually matters. She asked a very beautiful question. See, that is that, what if we were just lucky in this example? We were lucky that the flange in this example is class 3. Do you get? What if it's class 1? We can't calculate for web. We don't have FC. So I think the solution to everything is that we need to have FC. Assume FC. Assume FC. Eh? Just give it a value. Just like 1,000.
700.
They'll be coming from they'll be acting on the column. FC. From the beam. You know the slab beam column.
For this question, we don't solve for flange. Like we don't solve for web or in the game because we're
It's already classified. How is it classified?
the flange is very classified.
Exactly. But what if the flange was class 1? And let's say, and we don't know what the web is eventually. So we need to assume FC.
That FC over.
Yes. So I will just say that we are supposed to have FC.
So we classify
Sorry?
the flange
Yes.
semi-compact.
Yes. Yes. But what if in another case, we're lucky here. What if we had class 1?
Class one.
I want us to understand something. Wait. Please. Now, this class 1 that we got here, it was semi-compact and it was the weakest, right? We're lucky that it's the weakest that we have there because eventually it's still that weakest that we will use to classify the entire cross-section. But what if class 1 was plastic?
So,
And class 3, we don't know what the classification of the web is. Yeah.
Class one.
Yeah.
Class two.
Yes.
In the years of the road, they don't applicate class 1, class 2. And that will be class 3. It will be the weakest class.
Are you sure? They said not applicable. They said not applicable. Okay.
question. It's the turn you have used.
Okay, I've seen the mistake. Yeah, I don't see him. Now you think they talk to me. So it's obviously class 3. Why is it class 3? Go to the code. You see under Axial compression for flange and web. They said not applicable for class 1 and class 2. And they gave us something for class 3 for both. So obviously class 3 means it is class. So class 3 is semi-compact. Let's now proceed. This is the main thing now. We should have just done this in like 10 minutes or something.
And here we are. 4 points.
So, the next step now, let's start with the x-axis. The next step is the slenderness ratio. LEX over RX for x. And for this column, we have 7 meters. And they said pin at both ends. So it means that LE will be equals to 7. They said pin at both ends.
Pin at both ends. This is the board now. It's only position.
Restraint in position at both ends is the same as pin at both ends. That's what I said in the first this thing.
Restraint
in position at both ends is the same as pinned at both ends.
What's on pin at both ends?
Restraint in direction at both ends.
Sorry.
That's right.
Position is for
Now, before I move back, do we understand the section classification? Do we understand the section classification? Yes. It's very straightforward. I didn't realize that class 1 and class 2 was not applicable for axial compression for both of the flange and web. Do you get? So with this, it is very straightforward. You can just ask your guys around you. So, restraint in position at both ends is just like saying pinch at both ends. And effective length will be equal to the actual length. Right? Why is it equal? Check table 22. And I explained this initially, but check table 22. There's no time for understanding. Just put the... No, I already explained it already. So this will be LEX will obviously be 7 meters, right? Because it is the same thing as L naught as per pin at both ends. Remember, effective length is the distance between inflection points, point of zero moment. So 7 meters over, what do we have in our section table for RX?
18.4 centimeters. We are not hearing you.
Restrain the body. In position. Yes, in position means pinned. Yes. So RX is what? RX is what?
18.4.
What do we have? What do we have as effective length in the x direction? Sorry? Yes, I've converted it to that. So what do we have for y? Okay, we have this now. The next step is to go to our short curve. Guys, please let's listen. Let's listen. Short curve. Lambda x, LEX over RX. 18.4 times 10 to the power minus 2. 18.4, check your section table. To convert it into meters. It was in centimeters. Now, what is the maximum thickness for this section? Is 77 less than 40 or greater than 40? So in your notes, you are going to put greater than 40. What are we dealing with? An I section or an H section? The next step is to go to short curve. We're doing X first. We'll do Y. But now we have gotten our slenderness ratio. Please follow me, follow me, follow me. Follow me, there's no time. We have gotten slenderness ratio already, right? After slenderness ratio, where's the next one? Short curve. And that is what I'm doing here. Right? That is what I'm doing here. Please, I need Dosta. X, Y. Please, Dosta. Dosta. Please, give me something. So, in our short curve, we need the fact that it is greater than 40. We need the fact that it is an H section. Now, with these two parameters, and the fact that it is a road section.
How do you use H section?
Come now, I'll answer the question. Why is the road section? I mean, why is the road section?
Why is it road section?
Yes. One word.
Manufacture.
Because we're using universal column and row. So your question, why is it H section? Check your section tables. You will see that for beams, you'll be having 1000 by 500. That's obviously a dimension like this. Alright. But in H, you'll be seeing something that is very, very close. That is the flange dimension. Let me put it this way. That is your D is almost equal to your B. Something like 352 by 345 now, something like this. Check your section table. The values are close. Yes, so it is already looking like H. Something like this. See. This is almost the same direct distance.
So which dimension do you now to the man who dog that? Which dimension do you now use?
This and please, this is a section designation. It's not your dimensions. You will take this to your section table to get your dimensions. This is used to identify the section.
How do you
How do I know it? I'll do for Y also. So I'm still in x-axis. So what do we have here for this thrust curve? Which thrust curve are we using? Which thrust curve are we using for this condition? For x-axis. Because we're dealing with x-axis for now. Just one down. For what?
For x-axis.
Please, your question. Your question. Carry this to table 24. Carry this to table 24. Guys, I need your attention. There's no time. I'm really like, there's no time. Carry this to 24. To get our designs, to get our compressive strength. Yes.
Lesser than 110, okay?
Yes, carry C, the short curve of C.
It's C for the exact.
Carry short curve of C and slenderness ratio of 38.4.
So it's better than 40.
Carry these two parameters to table 24.
You interpolate.
Yeah, we will calculate. Can you give me the...
Can you imagine smiling example?
Okay.
Number is less than I'm allowed to
I'm looking for 40 then 30, no, 35, 35. Then 40 down. Under that 35. 221. Where are some doing that?
Have you solved it?
So what do we have here? What do we have here? Can somebody solve this?
My 216.
216, Abi. Please, can we reduce the noise? We're recording a video for this set, for the next set, for the next sets to come. So please, can we reduce our noise? So now, having known, hey,
It happens like that. It happens.
now that we know our compressive strength, we need to know our compressive resistance, compression resistance rather. So, big P, small p. This is our compressive strength. These are our compressive resistance. Do you get? So, PCX, small p, big P. Now, the compressive resistance is equal to compressive strength, small p, times AG. Now, I was not even giving you guys the section where it is in the table. But let's just continue first. I think this is a 4.7.7. I'm coming. Age is what? 805. So what do we have here? 10 squared to convert it to millimeter square, times 10 to the power minus 3 to convert it to kilonewtons. What do we have? $17.45. Are you sure? It's not small. It's small. Susan, are you sure? 216.744 times 805. Wow. Okay, let's come again. 216.744 times 805 times 10 square
It's correct.
is correct. So we do the same thing for y. What's up? What's up? So this formula came from section 4.7.4. 808. You got 805. When you calculated this, what do you do?
You correcting it to 8 degree.
You can search for my mistake for one. Because I was even thinking that how come our compression resistance is this small? I mean, we tried a very big cross section. You don't understand? We tried a very big cross section. How come it's this small? So what do we have? What do we have? Now, this you get from 4.7.4. Oh, from section 4.7.4. This formula. You get. Let's continue. Now, let's do y-axis. Let's do the one for y-axis now. Let's do y-axis. For y-axis,